Welcome to this puzzle session. Here is the puzzle we are looking at. So there is a flea on each square of a 5x5 board as shown. So what is flea? A flea is just some insect. I also don't know what exactly it is. And it's written F-L-E-A, but it is pronounced like F-L-E-E, and I might slip up and pronounce it as flea occasionally. But the correct pronunciation is flea. So there is a flea on each of these squares, exactly one flea on every square of this 5x5 board. And then at a particular instant, or let's say at the press of a buzzer, each flea jumps to a square adjacent to its original square. So what do I mean by adjacent? Adjacent is this. So suppose you have this square. These four things are adjacent to this square. This is not adjacent. So if we have this square, then these four are adjacent. And if we had this square, then these two things are adjacent, and so on. So adjacency happens only in the vertical and the horizontal directions, not diagonally. This is not adjacent. So two squares are adjacent if they share an edge, you could say. Anyway, so that's what adjacency means. And then we want to show, the problem asks to show that after this jumping has happened, then there will be some square which will be over-occupied, meaning it will be occupied by more than one flea. So originally there was exactly one flea on every square, but once you make a jump, once every flea makes a jump to an adjacent square, then at the end of this jumping bonanza, there will be at least one square in which there will be at least two fleas. Okay, very interesting puzzle, and I will be presenting two solutions of it. And before I present any of the solutions, you should try these on your own. All right, so for the first solution, which I really like, it's like a amazing one-shot idea. So, okay, let me explain the solution for a 3x3 grid. This was a 5x5 grid, but doesn't matter. We can appreciate the main idea in 3x3 grid. So let's see. So we have this 3x3 grid, and the same thing. There is a flea on every square, and at the press of a buzzer, each of them jump to an adjacent square, and we want to show that at the end, there will be at least one square which will be over-occupied. So here is the main idea. The crux move is that we color the board with two colors. So this is sort of purple, but I will call it red, and this is blue. So we color it like we color a chessboard, red, blue, red, blue. Well, chessboard is colored black, white, but okay, anyway, red, blue, alternately like this. And the main observation is the following. Once we make this coloring, the main observation is this. In a jump, the flea changes the color of the square. So if the flea was sitting on the blue square, and if it jumps, then it jumps on and lands on a red square. So it changes the square of the color that it occupies. First it was occupying blue. After the jump, it is occupying red. Similarly, if you were sitting here, then the same thing. If you're sitting here, then the same thing. If initially you were occupying red, but now you're occupying blue. Wherever you go, whichever path you take, whichever jump you make, you're occupying a different color square. So that's the main idea. And now we can see what's going on. So now we have 5 fleas sitting on these squares, the red squares. And once they make a jump, all of them will be sitting on blue squares. Right? That's what we just observed. But the number of blue squares is less than the number of red squares. That's how this coloring is. So 5 fleas will now be occupying 4 squares. And now if you want to use the pigeonhole principle, you can say that, well, since there are 4 cages and 5 pigeons or 5 fleas, there should be at least one cage which hosts at least 2 fleas. Or you could just use common sense. So therefore, at least one of these blue squares should occupy at least 2 fleas. And that's it. That's the solution. And of course, this has nothing to do with 3. You could start with any odd cross odd board, meaning rather any n cross n board where n is odd. So in that case, what will happen is the number of, one color will exceed the total number of the other colors. And that is basically the heart of this proof. So since this is in a 3 cross 3 board, 3 is the odd number, that's why this is happening. In a 4 cross 4 board, this won't happen. You'll see that the number of red squares is exactly equal to the number of blue squares. And in fact, indeed, there is, in a 4 cross 4 board, it is possible for the fleas to jump in a way that satisfies all the constraints of the problem. And at the end, each square is occupied by exactly one fleas. But in a 3 cross 3 or a 5 cross 5 or a 7 cross 7, this won't happen, and this argument makes it clear. So that's the proof. This is first solution. The second solution is the one. So basically, I did not think of this one. I thought of this other approach, which I call the graph theoretic approach. This is a more pedestrian approach, and it has more steps basically, and it is also a little bit harder to explain. So here is what we will do. We have this again 3 cross 3. I'll explain the idea in a 3 cross 3 board. So we have this 3 cross 3 board, and we will represent each square by a vertex in a graph. So for a basic primer in graph theory, you can follow the top right corner of the screen, and you'll be able to follow all the basic concepts. So each square here is now represented by a vertex. Okay. So we have these nine vertices, and now suppose first so assume that there is indeed a way for the fleas to jump to adjacent squares in a way such that at the end every square hosts exactly one flea. Suppose it were possible. Alright, so what we will do is we will just record that jumping scheme via edges. So there was a flea here, it jumped to an adjacent square, either this one or that one. So whichever one it jumped, let's say it came here just for the sake of explanation, so let's say it came down, then what we will do is we'll draw an edge like this and draw an arrow. So this arrow will record what happened to this guy, this flea jumped to this this square. Okay, and similarly we'll have an arrow because no flea stays on the same square. It is given that it has to jump to an adjacent square, so there is an arrow coming out also, and then there is an arrow coming out, and so on. So here is the first main observation. So we see that each vertex has exactly one arrow coming out of it. Exactly one outgoing arrow, so to say. This is simply because each flea jumps to an adjacent square. That's what this gives us. And exactly one arrow coming in. This is why the assumption that it is possible for the fleas to jump in a way so that at the end of the jumping, each square or each vertex has exactly one flea. So two fleas cannot be coming in the same thing. That's what our assumption is. We want to achieve a contradiction basically. So we have this. So this particular jumping scheme should satisfy these two constraints. All right. And now here is another. I mean, from just this observation comes another observation: is that if I just follow these arrows around, so there is an arrow coming out of it, then there is an arrow coming out, and then coming out, and so on. At some point, I have to come back to a vertex I've already visited, because there are only finitely many vertices. And as I walk along, I have to come back to some vertex again. Now it cannot be some intermediate vertex, because if this were the case, then this guy has this arrow coming in and that arrow coming in, so it will have two different arrows coming in. And that's not what's happening. Exactly one arrow comes in and exactly one arrow comes out. So we will reach back to a vertex that we have already visited, and that vertex has to be the starting vertex. So wherever we start, we will ultimately, close back to it. Okay, so this kind of thing is like a cycle. So basically we observe that each vertex lies on a cycle. If you know what I mean by cycle, it should be clear basically what I mean by a cycle. Further, two cycles cannot share a vertex. So if I have, let's say, this cycle and I have this cycle, well, this cannot happen, because then this guy has two incoming edges and two outgoing edges, and that invalidates these two constraints. So finally we observe that, or not finally, but we observe that the vertices lying on two different cycles are disjoint. So if you have two different cycles, then they do not share a vertex basically. Okay. So you could think of it as follows, that this set of vertices is getting partitioned into cycles, like this cycle, or here I can't draw it, but some other cycle. So maybe 3, 4, 5 cycles. I don't know how many cycles. Here there are very few vertices, so you cannot have too many cycles, but in a general setting where you have n big, then you could have a lot of cycles. But this should be satisfied. And now this is the final observation, that each cycle has even length. And this is also, once I write it down, it's not hard to see, because suppose I start here, then every time I come down, I have to make up for it by coming up. So the number of times I take a down edge, it's the same number of times I have to take an up edge to reach this level. And the number of times I take a right edge is the same number of times I have to take a left edge to reach this level. So therefore, the number of vertical edges is even and the number of horizontal edges is even, and therefore in every cycle, there's an even number of edges. So 1, 2, 3, 4, 5, 6, 7, 8, for example, in this particular cycle. So this implies, these two things imply that the number of vertices is even. And that's a contradiction, because n was odd. Basically 3 is an odd number, 3 cross 3 is 9, 9 is not an even number, so that's it. So it's a lot of steps, but perhaps it's more natural, at least it's more natural to me. At any rate, this solution also generalizes to any odd n. Take an odd n, this is fine, this works. And yeah, so very interesting puzzle. I hope we followed. And as usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening, and I'll see you next time.